In chapter 3, we finally start taking the derivative, which is the foundation of what Calculus 1 is all about. By now, you know that we've already defined to be the derivative to be an instantaneous rate of change. In section 3.1, we're still finding derivatives algebraically. And when you find derivatives algebraically, we depend upon what's called the difference quotient. And we take the limit of that difference quotient as the change in the independent variables becomes of negligible distance. So essentially, what we're doing in this entire section is we're saying an instantaneous rate of change, it's nothing more than an average rate of change over an infinitesimally small interval. So if I can keep on taking those average rates of change over a very, 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 very small interval, then they become an instantaneous rate of change. Notice the three definitions of a derivative that I have on this page. First of all, and this is our most common one, let's say I have some arbitrary function f of x, and my goal is to find out its instantaneous rate of change at a. So I want to know exactly what is the rate of change at a. I could look at that and say, well, it looks like your function is decreasing with maybe a slope of about -1 there. If you think about what y equals negative x looks like, it has a slope of -1. This has about a slope of -1, I would say. If I were just guessing what f prime of a is, I'd say, looks like it's about -1. But instead of guessing, we want to be able to find exactly what it is at that instant. So here's what we do. We say f prime of a is going to equal the limit as h approaches 0 of f of a plus h minus f of a over h. Now, think about what this formula is going to do. First of all, that numerator, f of a plus h minus f of a, all that's saying is that if I want to find out what happens at a, go to some point to the right-hand side of a and a distance of h units to the right of it, and then plot that point out. If I said, well, okay, f of a plus h minus f of a over h, where h is the distance in the x values, that would be the slope of this red line. Please remember, a line that connects 2 points on a curve is called a secant line. So we can say, well, this, without the limit, would just give me the average rate of change from a to a plus h. And if I asked you, well, would the slope of that red line do a good job of representing what's happening at the instant of a? Clearly not. At the instant of a, our function has a negative slope. On average, from a to a plus h, it clearly has a positive slope. I would look at that and say it's probably about a positive 1/3 or a positive 1/2 or something. But I know it's a positive slope. So I can say, well, that would do a horrible job. Well, all right, how do I make that average rate of change into a very good representative of what's happening at the instant of a? All I have to do is say, well, okay, instead of that point a plus h being so far away, what if it wasn't as far away? What if a plus h was here? Then you'd be finding the secant line between those 2 points. What if a plus h was even closer, right there? Then you'd be finding the average rate of change between those 2 points. How close is close enough? And the answer is infinitesimally close. This second point gets so close to that first point, we just say, well, it's the limit as h approaches 0. So the distance between the values is some non-zero value, but it's so small you can't even quantify it. So point a billion, trillion zeros and then a 1, some infinitesimally small distance. So then we can say, well, okay, then the average rate of change is going to give me a ridiculously good idea of what the instantaneous rate of change is there. And I say, absolutely wonderful. That is the definition of a derivative. Instantaneous rate of change at a is nothing more than the average rate of change from a to a plus h, but we're going to take that distance h and make it negligibly small. So I can say, okay, that is one definition of a derivative. Unfortunately, there's two more, but I need you to see it's no big deal. You can always, if you like this one, you can always use that one. But you'll notice in your book, they also mention this definition of a derivative. It's the same idea. And oftentimes students wonder why we have slightly different ways of saying the same thing. Well, remember, calculus was invented by two different people, and we try to give them both credit. Wilhelm Gottfried Leibniz and Sir Isaac Newton. And this is a result of that. If we look at another definition of the derivative here, I tried to draw my curve similar as to how it was drawn over here. And yet again, my goal would be find out what happens at A. Well, my goal is if I want to find out at the instant of A, what's the slope of that curve, I need to, again, find a point to the right of it and find the average rate of change from this point to that point. In this case, I just call the second point some arbitrary value of x. So then I can say, well, if that's some arbitrary value of x, the slope of this red line would be the change in the y over the change in the x. The change in the y would be f of x minus f of a. The change in the x would be x minus a. Please notice that's what this formula right here is. That's just your slope formula. That's the average rate of change from a to x. But now, if you wanted to change that average rate of change formula to be, tell me at the instant of A, what happens? Well, just take this second point and push it towards the first point. Please notice what your limit is doing. It's saying the instantaneous rate of change at A, or the derivative of f at A, is equal to the limit as x approaches A of this average rate of change formula. As x approaches A, this second point gets infinitesimally close to this first point, and as it does that, the slope of the secant lines that you're finding start giving you the slope of the tangent line at that point on the curve. It takes on the exact shape of the curve at that instance. So I can say, okay, that's our two main definitions for a derivative. Now, I will also mention this other one. What if you don't want the derivative to be defined at A? Typically, when we solve for derivatives algebraically, it is f prime of A, f prime of A. Some students would prefer to keep things in terms of x. So if you're one of those, notice what I did down here. I said both of these derivative definitions give the instantaneous, give the instantaneous rate of change of f at x equals A. Often it is preferred to keep the derivative in terms of x. Well, we can do that if we just say, well, if I want to keep this derivative in terms of x, why don't I call the point of interest some arbitrary value x? The point to the right of it, x plus h. And then you can say, well, then the slope of the secant line connecting the first point to the second point would be f of x plus h minus f of x, divided by the x values, which have a distance, again, of h units. You could say x plus h minus x. Of course, you get your h in the denominator again. And then you could say, well, yeah, that slope of the secant line can still be made to tell me what happens at the instant of x if I just allow h to go to 0. I want to take that second point and push it infinitesimally close to the first point. Remember, that is the unifying idea in all of these. I wanted h to go to 0. That took the second point to go to the first point. I wanted x to approach A. That took the second point, merged it closer to the first point. In each of the cases, you're going to smash that second point as close to that first point as you can, so your average rate of change starts getting measured over an infinitesimally small interval, and thus tells you the instantaneous rate of change. Now, you can use this formula if you would prefer to keep it in terms of x. Sometimes I do, but most of the time I think you'll find that I do this. I am fine with whichever one of these three formulas you do, as long as you can algebraically find the definition of a derivative. Now, speaking of that, let's go ahead and look at finding the algebraic definition. So let's say I give you a quadratic function here. F of x is equal to negative 5x squared plus 2x minus 8. And I asked you to find f prime of A And then once you find that, I want to know f prime of -3 and f prime of 4. Okay. Since I explicitly said f prime of a, I'm using the f prime of a function, and I chose the first one. My general rule of thumb is for all polynomials, I use f of a plus h minus f of a over h. If it's anything other than a polynomial, like if it's a rational function or a radical function, I prefer the f of x minus f of a over x minus a. I think they simplify a little bit more quickly in those problems. But if it's polynomials, I would just recommend using the f of a plus h minus f of a over h. You can always use whichever you prefer. That's just my general rule of thumb that I think it's the easier way to do it. So in this one, if I say, well, what is f of a plus h in this function? All you got to do is plug in a plus h everywhere you see an x. So you have -5 times a plus h squared plus 2 times a plus h minus 8. All of that is your f of a plus h. And remember, this derivative is still inside of a limit as h approaches 0. We subtract f of a, which is all of those same values, except you're putting an a in the place of x. And all of this is still divided by h. Now, the goal in all of these problems is to get rid of that h in the denominator. You cannot take the limit as h approaches 0 as long as you have a denominator of h. So I'll say, well, okay, I need to algebraically simplify my numerator. The group a plus h squared is going to be a squared plus 2ah plus h squared. And that's what I've done in this step right here. I really showed out my steps. And also notice I distributed the 2 in this step, and then I still have the -8 minus my f of a. Normally, if I were just doing this on my own, I would have never shown this step. I would have skipped from here to here. Now, what this step is doing is, yes, I multiply out the group a plus h squared, and now I'm distributing a 5 through each of the 3 terms to get to this. Again, you'll notice I'm keeping a bracket around my f of a plus h, and I'm keeping a bracket around my f of a. I'm doing that because now in this step, I need to start canceling out terms. And here's where I want to be extremely clear. The terms of f of a plus h and the terms of f of a will always, always, always cancel. Without exception, they always cancel. So if you're thinking, ooh, -5a and -5a squared, I'm going to make that -10a squared. Horrible. They never combine. So you say, okay, the signs should cancel out any common terms. -5a squared minus a -5a squared certainly does cancel. Then you go to the next term. Well, actually, let me go ahead and talk about all of the terms that cancel. 2a minus 2a goes away. -8 minus -8, they eliminate each other. And so then you're like, okay, so the terms of f of a plus h and f of a always cancel. What else am I promising will always happen? Right here. The terms that do not cancel will always have a factor of h. And you might think, well, John, how do you know they're always going to have a factor of h? Oh, I know they will. Why? Because that denominator has a factor of h. My numerator must have a factor of h, or it can't be canceled out and no limit would exist. So I'm saying I am 100% confident that any terms that don't cancel will have a factor of h. If I were doing this problem as we were talking, I would go ahead and put that h there and then open up my parenthesis and say, okay, what's the first term that didn't cancel? Well, the first term that didn't cancel was this one right here. Notice it has an h. If you factor an h out, you're left with -10a. You go to the next term. It didn't cancel out. -5h squared, if you factor out an h, will be a -5h. The 2a canceled. The 2h did not cancel, but if you factor an h out of that 2h, it leaves you with a 2. Now, this is an important step because we were wanting to take the limit as h approaches 0. You couldn't do that as long as there was a factor of h in the denominator, but in this step, you can see that, well, we can eliminate h because both of those will just cancel out, and we'll be left with the limit as h approaches 0 of -10a minus 5h plus 2, And then you say, well, what's my derivative with respect to a? Allow h to go to 0. It's going to drop out that second term, and you have negative 10a plus 2 for your final derivative answer algebraically with respect to a. Now, if f prime of a is negative 10a plus 2, how do I evaluate that at the other points, negative 3 and 4? Remember, a is just a specific value of x you're interested in. So you'd say, well, I'm interested in negative 3. I plug that in for a. I have negative 10 times negative 3 plus 2. That gives me 30 plus 2 for 32. If I wanted to know the derivative evaluated at 4, it's just going to be negative 10 times 4 plus 2. That's what I did here to get to negative 38. Now, in the last problem, it was second degree in power. As we start getting higher power in these polynomials, expanding out the a plus h can be problematic. And please don't be one of those people that say a plus h squared is a squared plus h squared. That inevitably always happens on the first calculus test, and it so annoys me. That's a heinous algebra error. A plus h times a plus h is a squared plus 2ah plus h squared. If you have to multiply it out by itself to get to that and FOIL it, please do. A quicker way is known as Pascal's triangle. And what Pascal's triangle is based off of is the idea that we know that any number to the 0 power is just 1. So I can say, well, a plus h to the 0 power is 1. Well, what if I had a plus h to the first power? You'd say, well, that's easy, John. It's 1a plus 1h. Yeah, 1a plus 1h. Now, a plus h squared. Every other row of our Pascal's triangle will start with a 1 and end with a 1. Every other number is the sum of the two above it. So please notice I start with a 1, end with a 1. 1 plus 1 is 2. So I can say, ooh, a plus h squared. This is going to give you the coefficients of the term. 1a squared plus 2ah plus 1h squared. What about a plus h cubed? Every row starts with a 1, ends with a 1. Any other number is the sum of the two above it. 1 plus 2 is 3, 2 plus 1 is 3. So what is this telling me? It's telling me that a plus h cubed is a to the third plus 3a squared h plus 3a h squared plus 1h cubed. What about a plus h to the fourth? Every row starts with a 1 and ends with a 1. Each other number is the sum of the two above it. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So what is a plus h to the fourth? It'd be 1a to the fourth plus 4a to the third h plus 6a squared h squared plus 4ah cubed plus 1h to the fourth. Then for the last one I'll look at here, what about a plus h to the fifth power? You say, well, again, John, it's the same pattern. Every row starts with a 1 and ends with a 1. Any other number is the sum of the two above it. 1 plus 4, 4 plus 6 is 10, 6 plus 4 is 10, 1 plus 4 is 5. So then I can say, well, what is this telling me? It's telling me that I am 100% confident in saying that the leading coefficient, when I expand out a plus h to the fifth power, it's going to be a 1a to the fifth. Now, every other term is a coefficient of the a and h's, where a continually decreases in power as h increases in power. The sum of the exponents is always 5, since this is 5. So you say, okay, 1a to the fifth plus 5, lower the power on a as you increase the power on h. 5a to the fourth h plus 10, a cubed h squared plus 10, lower the power on a, increase the power on h. 10a squared h cubed plus 5 ah to the fourth plus 1h to the fifth. Beautiful, beautiful. Pascal's triangle is just gorgeous. And a lot of teachers don't go over that as much as they should. It really helps out in some of these problems. For example here, let's say I give you one like this and I ask you to find the derivative algebraically. I want you to find f prime of a if f of x is equal to x to the fifth plus 2x cubed minus 5x. I want you to find f prime of a, f prime of negative 5, and f prime of 2. Okay, limit definition of a derivative, then I can say, well, all right, this is the limit as h approaches 0 of f of a plus h. Everywhere you see an x, you put an a plus h. So I have a plus h to the 5th plus 2 times a plus h cubed minus 5 times a plus h. Of course, minus f of a is just going to be minus the group a to the 5th plus 2a cubed minus 5a. Now, the bulk of the work in this problem is expanding each of these terms out here. The a plus h to the 5th is what we did on the preceding page, so you can just pull that in. So I can say, okay, here's my a plus h to the 5th. It ends in that term. Now, I know that a plus h cubed, that's just my a cubed plus 3a squared h plus 3ah squared plus h cubed. We're multiplying that by 2. That's where you see the 2a cubed plus 6a squared h plus 6ah squared plus 2h cubed. Distribute the 5 through the next group and we get minus 5a minus 5h. Again, we still have minus f of a. From this step to this step, here's where I'm always wanting you to remember the terms of f of a and f of a plus h always cancel. And any terms that don't cancel out will have a common factor of h. So from this step to this step, I went ahead and put my common factor of h and then said times. Well, the a to the 5ths cancel out. This term doesn't cancel. In fact, the next term that cancels isn't until 2a cubed. So all other terms until this 2a cubed remain in there. Well, notice they all have a factor of h. I factor that h out, I'll have 5a to the 4th. Then I'll have plus 10a cubed h to the 1st plus 10a squared h squared plus 5a h cubed, and then plus h to the 4th from that term. My next term, 2a cubed minus 2a cubed canceled. Then I had the 6a squared h term didn't cancel, but you factor an h out, it becomes 6a squared. 6ah squared term didn't cancel. You factor out an h, it becomes 6ah. 2h cubed becomes 2h squared when you factor out an h. The minus 5a canceled out with the term of f of a, so cancels, cancels. Last term here, minus 5h didn't cancel, but again, remember, you need to factor an h out of all those terms. When you do, it just becomes minus 5. Now, all of this is over h. The whole point I factored the h out of those terms is so that we could eliminate h in this step in the problem and say, well, this is just going to become the limit as h approaches 0 of the expression I had in parentheses up here, but now it's no longer in a fraction. And then you can say, well, I can now take the limit since that h has been canceled out of the denominator, and I can allow every h term to be a 0. So that means the 2nd, 3rd, 4th, 5th, 7th, and 8th term all cancels out. Any term that had a factor of 0 cancels out. So you're just going to be left with 5a to the 4th plus 6a squared minus 5. You can say, okay, that's our algebraic derivative with respect to a. Now, I have the f prime of a defined. If I wanted to know f prime of negative 5, you just plug a negative 5 in for a, and you'd have 5 times negative 5 to the 4th plus 6 times negative 5 squared minus 5. The first one is the same thing as 5 to the 5th power, which is 3125. Then we have plus 6 times 25 is plus 150 minus 5. Gave me 3,270. Got pretty large there. For the f prime of 2, you just evaluate your algebraic derivative with an a value of 2. You'll get 2 to the 4th is 16 times 5 is 80. 2 squared is 4 times 6 is 24. So we have 80 plus 24 minus 5, 104 minus 5, 99. Now, as I said, I think before the beginning of number 1, for polynomial functions, I would always recommend the f of a plus h minus f of a over h. For rational and radical functions, if you're like me, you'll think that the other formula simplifies a little more easily. There's not much of a difference. But for rationals and radical functions, I'll always try to use this other limit definition of a derivative, let's look at a couple of examples with those. So first of all, a rational function. If I have f of x is equal to 7 over x minus 2. Again, I want to find f prime of a, and then a couple of values where I want you to evaluate the derivative. So first of all, we're using f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Okay, as I apply my problem to this, I can say, well, f of x is just my 7 over x minus 2, minus f of a, it's the exact same thing, except now there's an a in the place of x, so it's minus 7 over a minus 2. All of that's being divided by x minus a, and of course we still have to keep this inside of a limit as x approaches a. When I have this, I know that the goal of this problem, just like the goal in the preceding problem, was I have to cancel out that h in the denominator before I can allow it to be 0. Well, now the goal is I've got to cancel out that factor of x minus a. So there's no way to do that yet, so I simplify my numerator and say, I do not want to have compound fractions within the fraction. So you just say, okay, multiply by the least common denominator of any denominators you see in there. That's going to be x minus 2 and a minus 2. So you'll see I'm multiplying by an understood 1. The factors of x minus 2, a minus 2 in both the numerator and denominator. When I multiply by those factors in the numerator, the x minus 2 cancels out the x minus 2 in this denominator, but you're going to be left with 7 times a minus 2. And then you'll have minus 7. The a minus 2 would cancel with this one, but you're going to have minus 7 times x minus 2. Now again, this is inside of a limit as x approaches a. In the numerator, we are distributing and carrying out the multiplication to each of those terms. In the denominator, please do not. It would not be wise to say, well, can I distribute x minus a into these? No, please don't. Why? The whole point of this problem is to cancel out the factor of x minus a. And you lose sight of the fact that you need to do that if you start distributing in the denominator. So you'll notice I just left the denominator factored. It's going to be x minus a times x minus 2 times a minus 2. Now, in the numerator, I know the terms of f of x and f of a should have some cancellation. So let's multiply out and see what happens. I distribute my numerator. I have 7a minus 14. Then I would have negative 7x plus 14. Please remember, terms always cancel, never combine. So if you make a sign error here and say, well, what if I forgot that parenthesis and thought that that was a minus 14 or something? You would know that the minus 14s would never combine to give you negative 28. They have to cancel. There's no option. So you say, okay, negative 14 plus 14, as proper algebra dictates, they do cancel. And then you're going to have 7a minus 7x left over in that numerator. Seeing that, I just quickly say, well, I could factor a negative 7 out of that group, and if I did, the x would be positive and the a would be negative. So that's what I've done from this step to this step. So I said the 14s cancel. If I factor a negative 7 out of the x and the a term, it leaves me with x minus a. Why did I do that? Hopefully you see, because the gorgeousness happens there. I can say, ooh, factor of x minus a in the numerator, factor of x minus a in the denominator, x minus a's goes away. And we can say this is the limit as x approaches a of negative 7 over x minus 2, a minus 2. Then you can say, all right, once I factor out that factor of x minus a that was causing difficulty in the denominator, surely we can take our limit now. Sure, we've reached the limit of this problem. We can allow x to go to a, so that means everywhere you see an x in this problem, go ahead and put an a in its place. You're going to have negative 7 over a minus 2 times a minus 2. That's better written as negative 7 over a minus 2 quantity squared. That is our gorgeous algebraic definition of a derivative answer for f prime of a if f of x is 7 over x minus 2. We can say our derivative is going to be negative 7 over a minus 2 squared. Now, if I evaluated this derivative at 0, You can see, well, if you evaluate at 0, this is just going to be -7 over -2 squared. That's going to be -7 over 4 because -2 squared is a +4. What if I evaluate it at 5? I could say, okay, no big deal. If you plug a 5 in there, your denominator is going to be 5 minus 2 quantity squared, which is going to give you 3 squared. 3 squared, 9. Your answer is going to be -7/9. Interestingly enough, this derivative is always going to be negative because it's impossible for your denominator to be a negative term. So you're always going to have a negative numerator over a positive denominator. The slope of this function is always decreasing, which means this function is what we call a monotonic function. It's decreasing for all values of x that it exists on. So it's going to have a negative slope forever and ever and ever. It's a monotonic and decreasing function. Now, if you see my last question up here, I asked, why would f prime of 2 not exist? Hopefully that's pretty obvious here. You say, well, f prime of 2, that would be the slope of the curve when x is 2. A curve can't have a slope at a certain x value if it doesn't exist at that x value. Please notice this function has a vertical asymptote at x equals 2. It does not exist at x equals 2. Therefore, the derivative does not exist at x equals 2 either. And you can see that in your derivative formula. You can say, well, for what value of a could you not plug into that? And it's the same as the original. You say, well, the derivative would be undefined at a value of x or a is equal to 2. So you can say, all right, does not exist in the original, then it doesn't exist in the derivative. So any domain restriction on the original function will be a domain restriction on the derivative as well, because it's just representing the shape of the original function, and it can't represent the shape of the original function when the original function doesn't exist. For our last problem here, let's look at a radical function. So I'm giving you a square root, and I'm asking you to find f prime of a, and then evaluate the derivative at 4 and evaluate the derivative at 25. So I'm using the limit as x approaches a of f of x minus f of a over x minus a again. Then I can say, well, this is the limit as x approaches a. It's very easy to plug in f of x. Well, you know it's the root of x. F of a is just the root of a over our denominator x minus a. And then you can say, well, we know that this needs to be simplified out. I'm going to go ahead and multiply by the conjugate of the numerator. And again, the goal of everything I'm doing, it's with the hope of canceling out that x minus a in the denominator. So I multiply by the conjugate in the numerator, the square root of x plus the square root of a. And I can say, well, this is going to equal the limit as x approaches a. And I should have said I multiply by an understood 1. You multiply by the root of x plus the root of a in both the numerator and denominator. Notice in the denominator, I leave it factored. I don't start saying, well, can I call this x on the root of x plus x on the root of it? That would be horrible because it would hide the fact that that x minus a needs to cancel. So I leave the denominator factored. In the numerator, I multiply it out. The root of x times the root of x is x. Your middle terms would be plus xa minus xa. They always cancel when you multiply by the conjugate. Your last term is going to be a negative root of a times a positive root of a. That's minus a. And you can say, well, this is glorious because now our numerator has the exact term that needs to be canceled in the denominator. The x minus a's go aways. And then I can say, well, then this f prime of a, this is the derivative evaluated at a, it's equal to the limit as x approaches a of a numerator that's understood to be 1 now over a denominator that just has the factor, the root of x plus the root of a. At that point, since this x minus a was canceled out, you can go ahead and evaluate your limit and say, wherever there's an x, replace it with an a. You'll have 1 over the root of a plus the root of a, which is going to be 1 over 2 on the root of a. That's my final derivative, algebraic answer to the derivative. And I can say, well, okay, I've got that. Now, if I evaluate the derivative at 4, and I specifically chose values that had nice square roots here, 1 over 2 on the root of 4, that's going to give you 1 over 2 times 2 for 1/4. If you evaluate the derivative at 25, you'll have 1 over 2 on the root of 25, and you can say, well, that's just 1 over 2 times 5, 1 over 10. Now, that's giving you the slope of the curve at any of these points. So for example here, guys, let me show you here. If I took a square root function here on your calculator, I'll say y is equal to the square root of x. Let me go into the window here. I want to see all of the values that I have in this problem. Let me go from 0 to, I'll go to 35. And then our y values, just to see the x-axis in there, I'll go -1, and I'll go up to a value of 6. This should be fine. So here's my square root function in there. Now, whenever we're taking the derivative, we're finding the instantaneous rate of change of the curve at that point in time. Excuse me, guys. Ooh. So what I'll do here, if I can get my voice back, is go in and say, ooh, trace, if I look at the x value at 4, I don't know what happened there. I can say, well, yeah, clearly the square root of 4 is 2. That's just the y value there. But if I ask you what's the slope at that point, notice I can go second calculate. I'm going to find the derivative, second calculate 6. And please notice on the calculator, it's dy dx. That dy dx, it means the infinitesimally small change in y over the infinitesimally small change in x. In other words, instantaneous rate of change. So the instantaneous rate of change of y with respect to x, second calc 6, and we're trying to find out at 4. So you hit x equals 4, and it tells you, well, your derivative there, and we already knew the answer was 1/4, 0.25. Well, now let me go over here to my other value. Sorry, guys. If I find the derivative at 25, I can say, well, all right, just second calculate the derivative. When x is 25, it should represent the slope of the curve at that point, and you get your 0.1, which is 1/10. Now, a lot of the Achieve homework assignment has us finding the derivative and the equation of the tangent line at a certain point. Let me show you that the calculator can even do that. This kind of takes some of the fun out of those problems, though, so I would rather you just do it all by hand. But the calculator can help. You can go second program to the draw menu, and you can tell it to draw a tangent line. So if I wanted to know the tangent line to the square root of x at the point when x is 25, this is all I would have to do. Draw a tangent line, second draw, number 5. Tell it the x value that you want it to be tangent to. So I can say, well, I will need it an x value of 25. It's going to draw a line that takes on the slope at x equals 25, which we know is 0.1. And it's going to draw a point through that curve and use that slope forever and ever and ever. Now, I know as I keep on going on out that this line is going to intersect. It's not going to take on the same shape of the curve forever and ever. That square root function is going to more flatten out than the linear function will. But I can say it's going to touch that at one point and take on that direction forever and ever and ever. And you can see your equation down there. My equation of the line tangent to the curve at x equals 25 would be 1/10 x plus 2.5. All right, guys, hopefully that helps, and hopefully I don't lose my voice anymore like I did just a minute ago. Be well, and let me know if you have any questions.